Hello. Hi. Can everyone hear me? We'll just wait maybe 1 or 2 minutes for more people to come. Um, so you guys all have the notes that I sent? Anyone doesn't have the notes? Okay. So I know we talked about a bit of the notes during the previous open class, but what I'm gonna do is I'm just gonna start again from the top and just restart it, maybe at a little bit of a slower pace. So yeah. Okay, and the thing about physics is to explain physics, I have to say a lot of things, but to understand physics and write it down, you only need to write down very few things. So you don't have to write down everything I say. And suddenly you'll think that a lot of the words in the notes are useless, but one day when you're stuck and you want to understand the thing, you need all the words. So I'll prompt you what is important and ask you to write it down, but feel free to write down anything else or nothing else. Whatever you think about it. All right. So taking notes. Yeah, taking notes is quite important for this class because there's just a lot of content. I also recommend keeping a separate notebook, okay? Just because there might not be enough space to take notes on the paper. So I usually use I always find that I like to use like full A4 size notebooks. Okay, and then you can decorate it. And then every time you can write down stuff like this. So yeah, but up to small notebooks, big notebooks. All right, very good. So let's begin. Let's begin. So we're starting again on the motion. Okay. All right. Everyone can see the screen? Can everyone see the screen? Yeah. All right. Good. All right. First, we have all the definitions. So the point about this stuff is that we want to separate out what we think we previously know, which is speed and distance. Okay, that's primary school stuff, speed and distance. And in primary school, you saw how complicated it was if the speed changed direction, right? And then the distance, you have to like separately calculate the distance and all that stuff. Did you guys have experience of that? So, here we are talking about more general thing, which is velocity and displacement. Okay, so what is that? So first of all, displacement is a vector of how far the object's current position is from the starting position. Usually we just call the starting position 0. And, in one dimension, that would just be positive side or negative side. And then in more dimensions, it would be a vector, so a direction, an arrow sort of thing. Okay. So this is basically an arrow, right? So you have, let's say, 5 meters at this arrow at 45 degrees angle, you would say. Okay, and this thing can move around and we can keep track of its displacement, okay, which is what we really care about. Next, the word rate. Every time you see the word rate, it means the change over 1 second, change over some period of time, depending on your unit of time, but usually we use seconds. Motion means it's moving, so your position is changing over time. Now, previously in primary school, when you had speed is what is called a scalar. So it's a number, okay? And this number, the important thing about a scalar is it's actually always a positive number, and it doesn't have a direction, okay? So your speed is just 56 kilometers per hour. It doesn't, if you just say speed, I don't know if you're going left, right, up, down, you know. So now we keep track of the direction and we call it velocity. So velocity is a vector again, so it has a direction and a magnitude, right? So it's another arrow, okay? So now given an arrow, so for example, 20 degrees here, so you know the direction and also the magnitude, 56 kilometers an hour. In one dimension, it's only plus or minus, so it's the real axis. It can be plus or minus or 0. Okay, so basically what we've done is we have introduced direction to all of the stuff. And because we've introduced direction, you need to keep track of, in one dimension, you need to keep track of plus and minus signs. In 2 or 3 dimensions, you need to keep track of the whole vector itself. And we will learn how to deal with vectors later, like in a later chapter. But for this chapter, we only have plus or minus direction, so left or right. Okay. So what we call uniform motion is motion with a constant velocity. So a constant speed and constant direction. Okay. So for example, if you're moving always in like a curve at 56 kilometers an hour, this would not be uniform motion because it keeps changing the direction. Okay. So really uniform motion just means straight line. So straight line, yes. Curves, no. All right. So you can see in the diagram below, okay, if we take the right side as the positive direction, then moving to the right will be positive speed, positive velocity. Moving to the left will be positive speed, negative velocity. And if you come back around to yourself, the starting point, then you have positive speed, but the average velocity is 0. Yeah, so get rid of the word linear there. I think that probably confuses things. But yeah, average velocity is 0. Because you came back to where you started, there's no displacement, like displacement is also 0. Okay, does everything make sense so far? Can you guys react or type in okay or something? Okay, very good. Moving on. So now units. So this is a very simple table. It just says the units for position, distance, displacement, height is all meters, and then the velocities are meter per second. That's what we use. So MKS stands for meter kilogram second, and it's actually the predecessor to SI units. So SI units, are 7 units. MKS is just 3 units, so it was before SI units was set up anyways. So usually we would write X as the position and D as the distance. Now, I'm actually going to introduce some slightly different notation here. So I'm going to write S here as the displacement. Okay. Just in this case in one dimension, because I want to separate out from this one, which is also D. Height is still h, velocity is v, average velocity is. So average means there's a bar on top. So the bar means average. Okay, and I want you to also write down u, which is the initial velocity. Now, when I print the notes, you can see a bolded word, but of course you can't write bolded letters, so it's fine. But you just remember to write an arrow to indicate that it's a vector. But of course, later during calculation, it doesn't really matter what you write. Don't write the arrow. Okay, so what is average velocity? So average velocity is simply the displacement over time. So the change in the position over the time. Okay, so we will write it as change in x over change in time. Okay, so again, please do not memorize this, because the way that I'm writing down this equation is I'm just writing down what makes sense. So what average means. Average velocity means change in displacement over the change in time, right? So, yeah, I hope it just makes sense to you without needing to memorize this, okay? So velocity causes change in displacement over some time. Now, it actually, if you think about it, that is the average velocity, but if you try to average it over a smaller and smaller and smaller time scale, you will get the actual velocity. Okay, and that is what we call a derivative, but you guys don't know about derivatives, so we will skip this part. It's just fun reading. So, the displacement, okay, is going to be the average velocity times the time. And if you started at some position x0, then you need to add that to x0, and you get your final displacement, x0 plus vt, which really says that the change in the position x minus x0 is vt, average v times t. Okay. Again, no need to remember any of this, because these are just formulas we write down because of what we say, right? They are not like, universal truths or whatever, because if you have a different situation, you might write down something else. So there's a philosophical difference here. I don't know if you think about it this way, but in math, when you're doing actual math, the equations are unchangeable, right? You just have formulas, and then you use the formulas to do stuff. In physics, we rather like to write our own formulas. So it's actually the biggest part of challenge about physics is to write down your own formula of how you think the system will move. Okay, so there's always very general formulas, but how exactly you think it's going to work, you have to write it down yourself. So yeah. Okay, good. Next we have what does this dx dt actually mean? Okay, so by the way, this triangle thing is called a delta. But so what does delta x delta t actually mean? So it actually means the slope of the graph of position x against the time t. You raised hand? Somebody raised hand. Okay, so you have a graph, and then the slope, the slope is the velocity. You guys know how to find slope, right? You in your graph, you draw a tangent line. So to find slope, you draw a tangent line. Then you draw a triangle. Sorry, I don't know why I put 3 after 1. You draw a triangle. Okay, and then you call this thing dx dt. Okay, so for example, if you have a curved velocity line instead, okay, you would draw a tangent line here. I mean, if you're interested there. Okay, and then draw out a bigger triangle. It doesn't matter what triangle size you draw because it's going to be the same answer. Usually people just pick the triangle size to be convenient size. Okay. Right. So the units are going to work out because position is in meters and time is in seconds. And if you take dx, the change in x divided by change in t, you're taking meters to divide by seconds, and this is going to give you meter per second. So that is the units of velocity. Okay. In the following example, you can see that the thing has moved up. I mean, the displacement has increased and then flat and then decreased. So what is the velocity? So in the first one, you know, the triangle is incredibly easy to draw. It is just the entire thing. Okay. But of course, you can choose if you want to draw a smaller triangle, and then you have a very sad time trying to read off what are these values. So which is why I said usually you draw the triangle to be convenient. So draw it onto a grid point so you can actually read it off. Okay. And you will see that it says it increased 8 meters over 2 seconds. So 8 divided by 2 is +4. Okay. So how would you write that? Let me write it down. So my standard way of writing this would be the velocity is change in displacement or change in position over change in time. Okay, and to emphasize that this is a change, okay, I'm going to write this as 8 minus 0 over 2 minus 0. Now, you may think this is pretty unnecessary, and it is, and I will not write this again, but I just want to point out to you that we started at 0, then we went to 8. Yeah, but this is sort of the standard school way of writing a gradient, and whatever in terms of presentation, just do whatever the school tells you to do. Right? Okay, so some schools will force you to write final minus initial divided by final minus initial. Some schools don't really care. Yeah. Okay, so moving the next bit now, you can see that there's no gradient. Okay, it's just always no change. So it's next one is going to be just 8 minus 8 divided by 4 minus 2, because from time 2 to time 4, you went from 8 to 8. So 8 minus 8 divided by 4 minus 2, and this is 0. Okay, and the last one, we have it decreased. Okay, so it started at 8, ended at 0. So 0 minus 8, and then it started at time 4, ended at time 8. So 0 minus 8 over 8 minus 4, this is minus 2. Okay, let me know if this makes sense. Okay, very good. So Okay, so example problems. A car travels 1,200 meters in 60 seconds. What is its average velocity? Then it's 1,200 divided by 60, which is 20 meters per second. A person walks 320 meters at an average velocity of 1.25. How long did it take? So 320 divided by 1.25 is 256 seconds. Okay, these are, I hope, very standard to you, right? Okay, next. All right, I forgot to put a line break in here, but you could draw a line here. So next we talk about acceleration. So what is acceleration? Acceleration is the change in the velocity. So if the velocity is increasing, we say it has positive acceleration. If the velocity is decreasing, we say it has negative acceleration. So if you look at the graph, in the first graph, the velocity is going up. The second graph, velocity is always the same. And the third graph, the velocity is going down. All right, so that will be positive acceleration, 0, and negative acceleration. Now, just to note that the way we say acceleration could be slightly different. Okay, so for example, if the velocity, a positive acceleration could mean that the velocity is getting less negative or more positive. And that really means the same thing, right? If you're saying a number increases, it could be less negative or more positive. It's the same description, okay? So in this example, for example, your object is moving to the left and it slows down and it turns around and moves to the right. This would be positive acceleration if you said right was positive. So since velocity was meter per second, acceleration is now meter per second square because you divide by time again. All right. And we usually use G for gravity. Now, again, the same story happens, and we say acceleration is the change in velocity over some time. So it's going to be delta V over delta T. And if you take the time limit to 0, then you'll get the derivative of V over T. Right? So, okay, we're going to skip this calculus bit. So we're going to say, we're going to assume that the acceleration is always constant. Okay. So, of course, when we finish the whole course and we start back and learn calculus, we're going to come back to all this stuff. But for now, it's just fun reading. So we're going to say, okay, acceleration is constant for everything that follows. Okay, all the problems that follow. So what will be the change in velocity? It would just be acceleration times time. Literally the same as just now if we assume velocity was constant. Okay, so velocity, change in velocity is acceleration times time. Okay, if I say that the initial velocity is v0, then v minus v0 is at. Okay, in the same way that just now we said x minus x0 is vt. But that assumed that the velocity was constant. So you can see how different assumptions will change your equation. So what is the equations now? So the equation now is going to be, so I'm going to write this as u, okay? Because just to, I know you guys may not be very comfortable writing 0 below the v, so we're going to say initial velocity is u, final velocity is v, so v equals to u plus at. I moved it over to the right. Okay. If I write down something, please write it down as well. Okay, good. So the slope again, all right? The yeah. So acceleration is the slope of the velocity and time graph. So again, the triangle thing, draw the tangent, draw a triangle. So now we're going to look at what does it mean to be positive acceleration for the position. Okay, so we look at the first column, we have positive acceleration. That means the velocity is going up in time. What does that mean for the position? Well, in the first diagram we have, in this one, we have the velocity, which is the gradient, okay? It's initially very slow because the triangle is very shallow. And then as you draw more triangles, the velocity increases. Formula I wrote just now was this. I literally just rewrote this thing and moved the thing to the right. Okay. All right, so okay. So on the other hand, it could be that you were initially going in a negative direction, so your position is decreasing, your velocity is negative. Okay, and the velocity is initially very negative, and then over time, you know, you draw your triangle and the velocity is only slightly negative. So the velocity gets less and less negative, but that's really the same thing as more and more positive. So these are the two graphs that could possibly correspond to a positive acceleration. And in general, a positive acceleration just means that your graph is curving upwards. As you can see, both of these are examples of graphs that curve upwards. And people will call that a convex graph or a concave up graph. Again, depending on which school you go to and what textbook you read. Okay, so it's a smiley face, all right? Positive acceleration, smiley face. Now, second case, no acceleration, velocity always the same. So if velocity is always the same, the gradient of the position time graph is always the same. So it's just going to be a straight line. Nothing is changing. Okay? You don't really understand smile. Okay, so what I'm saying is both of these graphs curve upwards. Okay? So they actually are part of the same graph of a bigger, fully smiley face graph. So I'm trying to say that positive acceleration means that the graph curves upwards. And that means that the graph should be some part of a smiley face. Okay, let me just specify the position graph curves upwards. All right, it's just a way to remember it, like a description. Okay, okay. Okay, so zero acceleration, velocity not changing, gradient is not changing, straight line. Negative acceleration is the exactly opposite story. So the velocity is getting more and more negative over time. So initially, this velocity is slightly negative and then more negative and then even more negative, or it is very positive and then less positive and then less positive. So getting less positive is the same thing as getting more negative. Okay, and we can see that these graphs are curving down. Okay, so they are really part of a sad phase graph. Okay, so negative acceleration. Position graph curves downwards, and this is a sad phase. Okay, does that make sense? What does the bottom left chart mean? You mean this one? Are you talking about this one? Okay, so what does that mean? So okay, so we can see that at the start, okay, what is your velocity? Okay, if you draw your triangle, your velocity is very negative. Okay, so maybe it's like -10. And then later on, if you draw your tangent triangle, maybe it's only -5. And then later on, maybe it's only -1. So what it means is the velocity gets less and less negative. Okay, and that is an example of positive acceleration. So just note that in this case, it means velocity more positive. So these are under the case of positive acceleration. Okay, similarly, on the right side, you have velocity more negative and velocity less positive. All right, does any other questions? Does that make sense? Please ask questions. Questions are good. Okay, does that mean you guys are all happy? Okay. All right. So this is all of that is the idea of getting a slope. All right. Now we talk about the reverse idea. The reverse idea is the area under the graph. So since the velocity is the change in displacement, that means that if you sum up your velocity at every time, you're gonna get the change in displacement. So like, so the area under the graph of velocity times time, so will be the displacement. So in this case, for example, you have 5 meters per second for 10 seconds. That 5 times 10 is the area of a rectangle, right? That's the formula. Okay, and even if it's not a straight line, you just find the area under the graph, it would still work. Okay, so if you have some positive acceleration, the velocity is going up. The area under the graph is a triangle. If you find the triangle area, you will be finding the displacement. Okay, so the area under the graph is technically an integral. Okay, but again, we're not talking about that. And there are many formulas to find area under graphs. You know how to find area of triangle, trapezium, rectangles, and so on. So in the following example, we have this. So we have acceleration being 2.5. Okay, 2.5, as you can see, because it goes from 0 to 10 meters per second in 4 seconds. So 10 over 4 is 2.5. Now, what is the displacement? The displacement is, okay, the area under the graph. So in this first example, the area under the graph is half by 2 by 5. Half by 2 by 5, and that will be 5 meters. Okay. Ignore the middle line for now. In the second one, if you consider the big triangle, it will be half by 4 by 10. Okay. So 20. And in the rectangle, it is just 2 by 10. So 20. All right. So that is the area under the graph. And what we're trying to claim here is, and what we're trying to claim here is we want to observe that the result we got from finding the area is actually the same result if we use this mysterious formula. Okay, so half acceleration times square. But why? Why are we using this formula? Okay, so in this case, in this case, the area thing should make 100% sense, because the velocity is always the same. So velocity times time should clearly be the displacement, right? So 2 times 10 should make a lot of sense. Okay, but what is going on inside here? So we're going to the next page. Okay, now, so what is the formulas we have now? The formulas we have now is that displacement is the average velocity times time, right? But what is the average? It means that the average the velocity, and it is not so easy to find the average of velocity. But if the velocity is just changing like a straight line, then the average should clearly be the start and the end plus together divided by 2. Okay. So if you start off not moving, so 0, then your final velocity, let's say, is v, then your average velocity is actually only half v. Okay. And if your displacement is average velocity times time, then it will be half v times time. So, and then velocity is a times t, so half at times t, so half at squared. Now, what if it was moving before? So instead of half v, it is now v plus v0 over 2. So the velocity time graph looks like this. So it starts off at v0 and then it increases under the acceleration. What is the area using this formula? So it will be, I'll write the derivation here. The displacement is average velocity times time. So it'll be v0 plus v over 2 times time. Okay. But what is v? V is v0 plus at, right? Because if you have some acceleration, it will cause a change in your velocity. You add that to your original velocity, you should get your new velocity. So this is actually 2v0 plus at over 2 times time. And if you divide it over, it will be v0t plus half at squared. Okay, take a look at this. Tell me if it makes sense to you. So if it makes sense to you, I also want you to realize that this is actually exactly the same thing as the area formula for a trapezium, right? Because v0 is like the base, or maybe that's I don't know. It depends on how you calculate trapezium, but trapezium area is base plus top divided by 2 times height, right? So we have base, top, divided by 2 height of the trapezium. Okay, so I'm just saying that the formula of average velocity times time is actually exactly the same thing as the area of trapezium. And it should, if you do any calculation, it should give you the same result, which is a way you can double check. Okay, so my point is, it is the area under the graph. Even if the area under the graph is a triangle, a trapezium, a rectangle, whatever it is, the distance, the displacement moved is the area under the graph of the velocity and the time. Okay. Now, so all right. Can everyone type in okay if you have understood this, or please tell me if you want me to explain again. Everyone okay? Okay, very good. Now, now what I want you to do is I want you to grab a spare piece of paper, okay, like foolscap or something. And I'm just gonna write down, so this is now off notes, okay? I want you to copy all this stuff down. Okay, so what have we learned so far? So we assume, again, we still assume constant acceleration. Okay, and if we do that, and we say the initial velocity is u, the final velocity is v, the acceleration is a, the time is t, and the displacement is s. Okay, why I'm changing up the letters a little, because these are the letters that are used standardly in RI and NUS high. Why the notes was not in this notation is because I wanted to keep the vector sign on top of them, and you would not use S if you had, I mean, it's like there's a slightly different standard of notation if you're doing vectors or not. So anyways, so it's also good exercise to just change names, right? Change the variable names. So what have we learned so far? We have learned so far that okay, v equals to u plus at. So the final velocity is the initial velocity plus acceleration times time. And the graph looks like that. Okay, the graph of velocity starts off at u, okay, and after time t, it is at v. So please sketch all of this stuff. Okay, and we know that the displacement is ut plus half at squared, but also some people like to think about it like this. So average velocity times time. Okay, and in this case, it would be something like this. Okay, it's a curving up graph, and after some time t, it would have moved some distance s. All right, has everyone written this down? Has everyone written this down? Okay, so now what I want you to do is I want you to use the two equations, and I want you to prove b squared equals to u squared plus 2as. So I'd like you to try that now, please. Do let me know when you have proved it. Do you guys know how to prove stuff? I mean, I don't really need to be very rigorous at the moment, but yeah. Just give it a try. See if you can make both left side equals the right side by using the formulas we currently know. So again, these formulas, right? It sounds like we just made them up. And in a way we did, but I hope you agree that we made them up in a way that makes some sort of common sense. Okay. And this is basically classical mechanics, which is you just write down what you think it's gonna do. Now, when you get into university and quantum mechanics, none of this is gonna work. Everything is unable to be totally explained by writing down your equations. Like you are unable to specify what the particles are doing. You have to do it in a bit more indirect way. So yeah, so do enjoy this while you can. You can dictate. You can tell every particle what to do. Okay, you done. All right, very good. When you're done, tell me in the chat so I know. Um, or let me know if you're stuck and you need help. Okay, a bunch of people seem to be done. So, would anyone like to explain what they did? You can like unmute yourself and talk if you wish. Yeah, you can also annotate. Okay, so very good. So we know v equals to u plus at. So v square is u plus at square, and you expand out the square, which will be u square plus 2 aut. Is this in alphabetical order? A, B, C, D? No, it's okay, whatever. Plus a squared t square, and then you take out a 2a because the question says there should be a 2a, so you take out a 2a, you get ut plus half at squared, and this is exactly 2as. Very good. Thanks. So what did we just do? We got rid of the time, right? That's basically what we did. We got rid of time. So it turns out it doesn't matter what the time is, right? You don't need to know how long you push the particle for. You don't need to know how long you push the box. You just need to know the initial final velocity, the acceleration, you can get the distance. Or, if there are 4 variables here, if you know any 3 of them, you can solve the other one, right? So if we know, okay, this is an example of a sentence which you don't need to write down. Any 3 of 4 variables, VUAS, we can solve the other. Okay, very cool. So we've proved our first formula. Okay, and I would just like you to get another color pen and just circle all of these things, because these are going to be important formulas we'll use again and again. All right. Very good. Any questions so far? Is anyone not comfortable with the algebra that we're doing? I know some of you might be in P5 or something, so you haven't learned algebra yet. Okay, but right. So algebra is really the backbone of everything. I hope with more practice you'll be able to do more of this stuff. Okay, very good. So we've got the formula now. V squared equals to u squared plus 2as. Okay. Now when an object is falling because of gravity, we just say it's in free fall. Okay, and gravity is about 9.81. But sometimes the question will just say you use 10, and turns out gravity is different at different places of the Earth, because Earth is not a sphere. Earth is like a ellipsoid thing. So actually gravity is a bit less on the equator as well. Okay. Now there is this thing called jerk, which is the change in acceleration per time. In this class, we're not going to talk about this because we are always going to assume acceleration is not changing. All right, good. Okay, so we're done talking about the theory part. So that was the first 9 pages. What we're going to do now is we're going to take a 5 minutes break, and then we'll start doing these problems. Okay. So on page 10. So why don't we take a break now? Hello. Hello. Are you guys back? Okay, cool. So what we're gonna do now is we're gonna start talking about page 10, problem 1. All right. So again, I'm not too fussed about descriptions, like writing essays. That's you will do a lot of that in school. So I just want to know the numbers. All right. So please do question 1, A and B. Find the velocity between 2 and 4, 6 and 7, and 8 and 10. All right. Once you have the answer, you can message me, or you can just message. I don't know. Just let me know when you're done. All right, and now. Okay, great. So, in the first one, the thing has positive velocity, and between 2 and 4 seconds, you can see that we can draw a little triangle here, and we can see that it went from what? It went from 2 to 4 seconds, it went from 18 to 54. So here's how I will write it. I'll write it as 54 minus 18 divided by 4 minus 2. That's the vertical change over the horizontal change. Okay, and you should know that this should be 36 over 2, so 18 meters per second. Don't forget the units. All right, and it has constant positive velocity. Okay, so again, constant velocity. Try not to say constant speed because that doesn't mean anything. Like constant velocity implies constant speed, but constant speed doesn't imply constant velocity. So it's a weaker statement. Okay, between 6 and 7, okay, it's clearly not moving, so the answer is 0. Okay. So if you want to write something, you could write 72 minus 72 over 7 minus 6, which is 0, but you could also just write 0. I don't really mind. 8 and 10, anybody has an answer? So part C now, 8 and 10. Right. So the important point about C is that the velocity is negative. Okay. So between 8 to 10 seconds, we are from here to here. If you read off from the graph, you will see that it went from, what is this, 66 to 42. So you would write 42 minus 66 because it's final minus initial, 10 minus 8 over 10 minus 8. So this will be negative 24 over 2, so negative 12 meters per second. So please remember negative, okay? So it's always final minus initial. All right. This is sort of a standard way of writing it. Please always write it this way. Okay, type an okay if you're happy with this problem. Very good. Very good. Next. Oh yeah, okay, sorry. Before we move on, let me just ask you, based on the shape of the graph, can you tell me whether these 3 bits are positive or negative acceleration? So tell me 3, so in order, left to right, positive or negative acceleration? Okay, very good. So you can see that the acceleration here is positive and then negative and then negative, right? So again, one way you can tell is because we said positive acceleration should be the happy phase graph. So it's curving up. That's the first one. And curving down for the next 2. You could also see it just because we calculated the velocity already. We know that velocity starts at 0, then it becomes faster up to 18, and then it slows down to 0, and then it goes negative to minus 12. So clearly the velocity was increasing, then decreasing, then decreasing. Okay. I hope you're happy with that. So the acceleration is positive, negative, negative. Very good. Very good. All right, now we do number 2. So number 2 is the same problem. 0 to 2, 2 to 4, 6 to 9. So do part A, B, and C, please. I need the numbers, please. Go how. Okay, so very good. Everybody agrees that the first one is just at rest. The thing is velocity is not changing. Okay, so it's constant velocity, no acceleration. So I could write 6 minus 6 over 3 minus 2 minus 0. This is 0 meters per second square. Okay, between 2 to 4, we can see that it's now like this. So there is a change in the velocity, and the acceleration will be the final velocity, so 12 minus 6, the initial velocity, and then 4 minus 2. So it'll be 3 meters per second squared. So it has positive acceleration. And then the last bit is between 6 and 9, so it's here. Okay. And it went from 12 to 0. Okay, so the acceleration is 0 minus 12 over 9 minus 6, so it'll be negative 4 meters per second squared. So it's negative acceleration. Okay, very good. Yeah. All right. Good. Very good. Happy? Nice. Okay, now we have number 3. Okay, number 3 gives us a position time graph, and we are asked to sketch the velocity time graph. So what you need to do is you need to find the velocity for each of the 4 segments and then plot it onto the next graph. All right, give it a try. Let me know when you're done. All right, good. So in the first bit, what is the velocity? So we have this one, which is from 0 to 35 in 5 seconds. So that is gonna be 35 minus, sorry, from 10. So 35 minus 10 over 5 minus 0. This is 5. So the first thing will be at 5 meters per second. Okay. Then the next one is clearly at 0 meters per second because the thing is not moving. And then the next one is gonna be at 50 minus 35 over 15 minus 10. So that's 3 meters per second. So 3. And then the last one is gonna be it drops all the way down to 0. So 0 minus 50 divided by 20 minus 15 is minus 10 meters per second. So minus 10. Okay, so this is your graph. If you wish, you could add dotted lines here, but you also don't have to. So this is what you're supposed to plot. So you find the velocity in each segment. You find the velocity in each segment, and you just draw the horizontal bits. Does that make sense? Can everyone type in okay if you're happy with that? Suddenly, perhaps. Okay, sorry. So would you like me to clarify anything? Okay, fine. All right, moving on. So next one is sort of just a rough thing. So, sorry, somewhat makes sense. Reynold. Is there anything you'd like me to explain? All right, number 4. So in 1991, Carl Lewis became the first sprinter to break the 10-second barrier for a 100-meter dash, which is this. And here we have the data for his run. Okay, so first what we want to do is we want to just plot this thing onto this graph. Okay, so that shouldn't be too hard. You guys know how to plot this. Is it okay to draw so these parts of the graph don't exist. You can choose to draw them or not. It's up to you. Nobody really minds. Usually people might put some dotted line, I think. I mean, I would, but it's also okay not to draw the dotted line. Okay, anyways, plotting this stuff now. So how do you plot stuff? So you start at 0 is 0, you put a little cross. Then when the distance is 10, it's at 1.88. So you just sort of estimate where 1.88 is. Then at 20, it is 2.96, so very close to 3. At 30, it is 3.88, 4.77, 5.61, 6.45, 7. Okay, actually, you should try it out on your, like, don't copy me, but just try to plot them on your own paper. Okay? Let me know how that goes. Why do I use cross? Because can we use dots? It's just that in NUS High, the standard is a cross. It may be a different thing in other schools, but at least I use cross. It is completely up to your science teacher. Like whatever they ask you to do in school, you can just do it. I mean, I don't mind if you use dots, if you use boxes or triangles or circles or stars or whatever, I don't mind. But at least in NUS High, we use cross. So yeah, it's just a bit easier to see, I think. Like dots make it less obvious there's a point there, and crosses make it more obvious there's a point there. So it depends on the visual effect you're trying to achieve. Like if you have a line that passes through all your points, then maybe it is better to put a cross because otherwise you will never see your points. Okay, the next part is the extremely difficult part, which is to try to draw a line through it. It's even harder to draw on a tab. Okay. Right, so try to draw a line through it that just sort of smoothly connects them. Not like this, like connecting each one, but just sort of through them. Now what we want to do is we want to plot the velocity. Now, there's no way we can plot the velocity very accurately. So what we're only going to do is we're only going to find out what the final velocity is. So what I want you to do is I want you to use your ruler and I want you to try to figure out where did the velocity stop being a straight line. I would say between the fourth point and the last point, it's pretty much a straight line. Would you guys agree? You can probably also use the third point. But before that, it definitely is not a straight line, right? So that's what I mean by drawing a convenient triangle. So this is a very convenient triangle. It may not be the most accurate because, again, we do not know the velocity graph. We are just sort of guessing it, but this is roughly what the constant velocity portion of it. So it's first of all quite impressive that he can run at a constant final velocity. Secondly, what is the velocity? So since we have picked the last point and the fourth point, okay, all we need to do is take the difference. So it's 100 minus 30 divided by 9.86 minus 3.88. And if you have a calculator, this will be 11.7056. Okay, I'll just keep 11.7 meters per second. So it's very fast, okay? 11.7 meters per second. Good. So now we know that the final velocity probably is, after 3 point something seconds, is probably over here. Good. Now, the next part is just a heuristic question. Do you think that the first part of the velocity would look like this or like this? What do you think? Okay, can anyone who picked the second one give me a justification? We are always positive velocity. Right, we're drawing on the velocity time graph, so we are actually always positive velocity. Yes, positive position, yes. But what's the difference between the two lines that I just drew? It's the acceleration, right? The slope of the velocity time graph is the acceleration. So in this case, okay, what does that say? This thing says that the initial acceleration is the highest. And then the acceleration slows down and eventually the acceleration is 0. Okay, sir. So your smiley face thing only applies to this graph, okay? Only applies to the position graph. So we're just in a discussion now. There are no right or wrong answers, okay? But this pink line that I just drew is saying that the acceleration is highest at the start of the run and then slowing down and eventually 0. Let me just write it down. So option 1, acceleration is highest at the start, then decreases to 0. Option 2, what does option 2 say? Option 2 says the highest slope, the steepest bit of the graph is the highest in the middle. So acceleration is highest not at the start, but sometime in the middle. So I just want you to draw on your own experience of running, and I want you to imagine yourself running, and I want to ask you, do you accelerate the fastest at the start of the run or somewhere in the middle of the run? Like if I ask you to sprint for 50 meters, would you accelerate the fastest at the start or in the middle? So I would think at the start, right? Because at the start, so why at the start? Because at the start you are not dealing with, you have no speed, right? At the start. So you have no air resistance that you're dealing with, right? So yeah, and if you run faster, there's some point where your legs just can't push the ground very much because there's the contact time the ground is not very strong. So you know you're running almost as fast as your legs can move. So in some sense, your legs don't actually have enough time to touch the ground and push you for very long. Whereas the first step that you take will have massive acceleration because you're applying all the force, right? And you have no air resistance because you have no speed, no velocity. So I would think the number one is probably closer to the truth, which is that the acceleration is the highest just at the front bit. Now, okay, maybe I know it depends on people, right? Because some people may say, oh, my second or third step is the most accelerating because I can, once you start running a little bit, you might be able to push yourself better. Okay. Anyways, the point is, I would expect the acceleration to decrease over time because you run into more air resistance. That's it. Different people may have different experience of the start point. So it may be some people may say the first step is the fastest acceleration. Some people may say the second step or whatever. But I hope they'll all agree that after 10 steps, it's not accelerating very much. Okay, amazing. Type in okay if you are happy with all of this. All right, very good. Okay, so the next bit is also a very important bit. Okay, so it's about selecting the right equation. So we have three equations just now, right? We have v equals to u plus at, s equals to ut plus half at squared, or s equals average velocity times t, and v squared equals to u squared plus 2as. Okay, this equation we don't use very often, but it could be better than the other equations. So how do you use the right equation for the problem? First of all, the equation must contain the thing you want to find, right? You don't use the equation which doesn't, if you're asked to find the time, you don't use v squared equals to u squared plus 2as because it doesn't have time in it. You will never solve for time that way. And other than containing the variable you're looking for, it must also contain other stuff that you know and not other things that you don't know, right? So, for example, if they say start at rest, it means the initial velocity is 0. If they mean come to a stop, it says the final velocity is 0. If there's gravity, the acceleration is probably gravity. Okay, so, and you also try not to solve too many things. So let's say they didn't ask you to solve the time, and you don't know the time, so maybe v squared equals to u squared plus 2as would be good because you don't want to solve the time anyway. Okay, the next thing is vectors. So we're only dealing with one direction, so it's only positive or negative. So you must keep track of what is positive or negative. So at the start of a problem, you must always, well, as a beginner, you must always draw something like this that says right positive or left positive, depending on your problem. Your choice. It should not change the answer. And anything that's moving in that direction should be plus. Anything that's moving in this direction should be minus. Please keep track of that. Okay. Very good. You can read these words. Let me know if you have any questions. Let me know, okay, if you are done reading the words on this page. So it's just some summary of the stuff that we already said before. All right, good. So now we're ready to solve some problems. Okay, first question is very easy. A race car traveling at constant speed makes one lap around the circular track of radius 100. When the car has traveled halfway around the track, what is the magnitude of its displacement from the starting point? So displacement, okay? Not distance, displacement. Right, so the answer is very simple. It's just 200 because you have a circle, okay? You start out here, you go halfway around the track. Your displacement is this arrow, and it's going to be 200. Okay? Make sense? So the displacement is 200 in some direction across the circle. What is the distance? Well, I think it's going to be 100 pi, right? because it's 200 pi would be the 2 pi r. Yeah, the circumference. Okay, good. Number 2, an elevator is moving upwards with a speed of 11 meters per second. 3 seconds later, the speed is now 5. What is the average acceleration? Yeah, so it's clearly gonna be -2 because you end at 5.0, you start at 11, you divide by 3 seconds. So it's -2. So in this case, I will just make a little quibble and say this is -2.0 meters per second square. Simply because all the numbers they gave you have two significant figures, like 2 digits, so your answer can also be 2 digits, like in terms of precision. We will talk more about this. You will learn more about this in school, but I'm not too worried about it. Okay, very good. Number 3, a car starting from rest accelerates with 2.5 meters per second square. How far would it travel in 12 seconds? Um, Great. Why are you guys getting 195? Can you tell me you're working? Okay, now I'm getting so many different numbers. So what is the formula? The formula is S equals to UT plus half AT squared. Because you start from rest, your initial velocity is 0. Okay, so it's just half acceleration time square, and this is 180. Okay, somebody said 30. The final velocity is 30. So this will be 2.5 times 12, which will be 30. But that's not what the question asked for. The question asked for distance, so that'll be 180. Okay. Does that make sense? Renault, Yuhang, Bob, Gao Hao. Yes, you could also do average speed, so 0 plus 30 divided by 2, then times 12. That should also give you 180, yes. Yeah, so the word starting from rest means the initial is 0. All right, good. Good, very good. Nice. Okay. Number 4. A body initially at rest is accelerated for 5 seconds, and the final speed is 20. What is the acceleration? Okay, this should be fairly easy. It's just 4. I know. 4.0, I would say, but it's fine. Okay, that's it. Number 5. I mean, this is a very, yeah. If the answer is obvious, it should be obvious, and then you can just say. All right, number 5. An object starts from rest and accelerates uniformly in a straight line. After 10 seconds, the speed is 70. What is the acceleration and how far does it travel? Right. The first one is fairly easy. It's 70 divided by 10, so 7 meters per second square. How far does it travel? Okay, Robert, what formula did you use for part B? The trapezium one. Okay. Sure. So s equals to half at squared. Right? Again, this starts from rest, so again, there's no initial velocity. So half at squared, you can do that. So half 710 squared, which is would be 350 meters. You could also do the average velocity, so 0 plus 70 over 2 times 10. Okay, which you probably would do if they didn't ask you part A, because again, you don't want to solve for unnecessary things, so you don't actually want to know the acceleration in the first, if they ask you part B without part A. But anyways, so 350 meters. Is everyone happy with that? Is everyone happy with this? Good. Is anyone not following? All right. Number 6. A race car has a speed of 80 meters per second, and then you release a drag parachute. Do you guys know what's a drag parachute? So you have a car, you have a very fast race car. Okay. This is a horrible drawing. And then you release, basically like a jet fighter, you release a parachute to slow you down. So they do this on like those land speed record cars that can go, I forgot how fast they can go. They can go almost up to the, not speed of sound, right? Okay, you can Google it. Land speed record cars. Anyways, so the parachute causes a deceleration of -4. how far will it travel before it stops? What is the appropriate equation to use? Oh, okay. Robert raises a very interesting point. I'd like to hear more answers. How far would it travel? Um, you seem to that's not right. Okay, so what is the formula you guys used? Which formula did you guys use? You use half AT squared. Is there a way to do it without finding the time? Like, there's nothing wrong with finding the time, but I think it's just a good habit to avoid finding something you don't want to find because, in the future, in a few years, when the questions get way more complicated, you want to, be optimized. So we can use the formula v squared equals to u squared plus 2as, right? We know that the final velocity is 0. We know the initial velocity is 80. We know the acceleration is -4. And we can solve for s, which is 800 meters. Alternatively, you could find the, time. So v equals to u plus at. So 0 equals to 80 plus -4 times t. So that will tell you the time is 20 seconds. And then s equals to ut plus half at squared. So this will be 80 times 20 plus a half minus 4 times 20 squared, and it should also give you 800. But you can see that, with one equation, it is a lot cleaner. Okay. Now, Robert mentioned a very important thing, which is that actually this is time reversible. So if you start from 80 and slow down with a acceleration of -4, it is actually the same thing as starting from 0 and accelerating with 4. Okay, until you hit 80. It's just playing the movie backwards, right? So if you do that, actually it makes it slightly easier to solve if you want to do it the slow way, but the fast way makes no difference. So you could also say we can also play the events in reverse. So that means that the initial is 0, the final is 80, the acceleration is +4. Okay, what is the distance it will travel? So then the time is still 20, right? But this you can now just use half AT squared. So half 420 squared, and it should also give you 800. Are you guys following this idea that if you recorded a movie of this thing and you play the movie backwards, it will just be positive acceleration fall because you will see the thing going faster and faster, and the final speed is 80, the initial speed is 0. And then you can use s equals to half at squared without the initial speed because you set the initial speed is 0. All right, happy? Okay, so what I'm gonna do now is we hit the end of page 15, so we're about halfway through the notes. We're gonna recap what we did today, and then if you come back for next lesson, we'll continue on page 16. So what did we do today? We talked about displacement and velocity. Okay, these have directions, so they keep track of plus and minus signs. We talked about getting the velocity as the slope of the displacement time graph or the position time graph. We talked about acceleration as the slope of the velocity time graph. We talked about position, the displacement as the area under the velocity time graph. And we got 3 of these formulas, and we tried out how to calculate with them. Okay? All right, any questions for today? All right, if you have no questions for today, then yeah, then that's it. All right, good. Hopefully I'll see you guys next week.